So Yasu's going to give his fourth thing.
So far I have talked about mathematical aspects of subfactor theory, and today I'd like to talk about how to apply this machinery to conformal field theory. So Roberto will give more details about conformal field theory from tomorrow, but today I just set up some basic framework. So conformal field theory is a kind of quantum field theory. So I'd like to start with some mathematical formulation on quantum field theory. But so from a mathematical viewpoint, a quantum field is a certain type of an operator value distribution on space-time. But from a technical viewpoint, it's rather difficult to deal with operator value distributions. So instead of dealing with operator value distributions, we'd like to rather deal with operator algebra generated by observables in a certain space-time region. So we consider some space-time region, then we have observables there. Then each observable is represented by a self-adjoint operator, which might be bounded. But then we can look at the operator algebra, conformal algebra generated by these possibly unbounded operators. So in this way, so for each space-time region, we get the conformal algebra generated by these observables. So in this way, we get the family of conformal algebras parameterized by space-time region, and that is our mathematical object. So in this axiomatic mathematical approach, we want to axiomatize a family of conformal algebras generated by observables. So this is a general idea to study quantum field theory in the setting of operator algebras. But now we are interested in conformal field theory, actually so-called chiral conformal field theory. Then in the standard conformal field theory, we will work on the Minkowski space of space dimension 1 and time dimension 1, so two-dimensional Minkowski space. But we want to work on the chiral half of the theory. Then the entire space-time is reduced to just dimension 1. And also we make a compactification of the space-time. So our space-time is just one-dimensional circle. S1, the one-dimensional circle. This is our kind of space-time in our setting. So the space and time are mixed into one dimension. Then, for this picture, the circle, we take some interval, the open, connected, non-dense, non-empty subset. And the interval is just an arc of the circle. So each interval I is this space-time region. So for each I, we have a conformal algebra. Then, from a mathematical viewpoint, we impose some actions on this family of conformal algebras parameterized by a circle, parameterized by intervals in the circle. So some actions. The first action is that if we have a larger space-time region, then we get more observable. So it means that we have a larger operator algebra. That's quite natural. The second one comes from locality. So actually, so this S1 is the compactification of the light ray in the two-dimensional Minkowski space, as I said. Then In the two-dimensional Minkowski space, we have a notion of a space-like separation. We have one region and another region. If they are space-like separated, we have no interaction between the two regions, even at the speed of the light. It means that we have some observable there, another observable there. If they are space-like separated, we have no interaction between the two. So they commute. So this operator, they commute. Then this commutativity takes even a simpler form in this dimension of one-dimensional circle. So if we have two disjoint intervals I and j, then an observable in A of I and another observable in A of j, they commute. So the commutator is 0, so this is the commutator, the refracted. Then, so this is an action called locality. Then we have, in quantum field theory, we have a notion of some covariance with respect to the space-time symmetry group. And in this setting, the space-time symmetry group is a diffeomorphism. Actually, the orientation preserving diffeomorphism group of the one-dimensional circle. So this is a diffeomorphism group. And so we have a first notion of covariance. I will detail, but we have some projective unitary representation of this group on this Hilbert space. And then we have some positivity of energy. And some vacuum vector. I'm omitting some details, but we have some condition corresponding to the positivity of the energy and also vacuum vector, and also certain irreducibility. So basically, this is a set of mathematical actions. So from a mathematical viewpoint, we just want to study a family of fundamental algebra parameterized by interval I subject to these actions. So this is a mathematical setting. Then in this setting, actually, so each fundamental algebra is actually automatically a type 3 factor. Actually, the hierarchy with type 3 factor. Which I explained in the first lecture. So in this way, the hierarchical factor naturally appears in this context of conformal field theory. Then I'd like to explain how a subfactor or endomorphism naturally appears in this context. So then what we want to study is representation theory. So in this setting, so we have common Hilbert space which has this vacuum vector. So we have lots of continuously many fundamental algebras acting on the same Hilbert space. But from the beginning, but here we have a notion of representation, which means that these fundamental algebras act on another Hilbert space where we do not have a vacuum vector anymore. So for A of I act. Well, they are represented on another Hilbert space simultaneously. This is a notion of representation. And then we can define, say, irreducibility irreducibility composition of representation and that kind of thing. Then here we naturally have an endomorphism picture as follows. then follow. Actually, before that, actually, I need one thing that so-called hard duality. Let's consider an interval I. Then, so we have the complement, and we denote I prime. We denote the complement by I prime. So actually, the interior of the complement, but it doesn't matter. So I prime is just basically the complement. Then the locality means implies that A of I then if we consider A of I prime the other way, then they commute. So A of I is contained in the commutant of A of I prime. So this is just a consequence of the locality action. But then the hard reality actually says that we do have equality here. This is a consequence of these actions. That's based on Tomita-Takesaki theory, so it's quite non-trivial. But actually, so originally we assumed just the inclusion here. We required only inclusion here, but it turns out that we do have the equality.
Equality follows from which point?
I mean, the set of actions. So the set of actions in class.
All of them?
Yeah, all of them. Equality holds. Then using this, we can study representation for pi I as a representation. A of I on another Hilbert space, K. And we need a certain compatibility among pi i's, but basically this is a family of representation parameterized by the interval in the circle. That's the notion of representation. Then, so I recall that at the beginning I mentioned that for type 3 factor, any representation, all representations are unitarily equivalent. So we have only one representation up to unitary equivalence. Then, so we fix some interval I and consider I prime of A of I prime on another Hilbert space K. But then A of I prime acts on the initial Hilbert space say H from the beginning by assumption. Then the original representation of A of I prime on the original Hilbert space and this new representation are unitarily equivalent. Okay? Then up to unitary equivalence, we may think that they are really the same. H is the original Hilbert space. So we assume that so this I of I prime, so after fixing an interval I, we regard that this is the same initial representation. Then we look at the interval I, another one I prime. Then we look at an operator x in A of I, and here we look at another operator in A of I prime. Then originally, before taking a representation, we of course have commutativity by locality. Originally, we have this one. Then this commutativity should be also true after taking a representation. So we should have this one But then, for this part, for I prime, A of I prime, we assume that this representation I prime is really the original one. So we can identify this to be Y. And also this is Y. So it means that we get that pi I of x commute with Y. But then, this is true for all x and all y, these algebras. Then this implies that I of x is contained in the commutant of all y, that is A of I prime, and the commutant. But then the hard duality says that this is equal to A of I. So it means that for any x in K of I, the image under this representation is contained in the original algebra A of I. So it means that I is actually an endomorphism of this algebra. So of this type 3, one factor. So in this way, an endomorphism naturally appears from representation, and of course, this endomorphism gives a subfactor through the image of this endomorphism. So in this way, we naturally get a subfactor theory here. And actually, this kind of consideration is originally due to a Dobrick-Kahag-Roberts study in the 70s. So this is called a Dobrick-Kahag-Roberts endomorphism. Then we have a notion of composition of endomorphisms, and actually this really defines the notion of tensor product of representation. The composition of define the notion of tensor product of representation.
Did you use that you are on a circle? The fact that you're on a circle, it could be other regions, higher dimensional?
Not really. I mean, for the hard duality for another thing, we do use the fact that we live on the circle. And actually, some people try to generalize this setting to higher dimensional things, but not much success.
Yeah.
In this way, an endomorphism composition, which is studied, naturally appears in this section. Then, we studied notion of braiding for a system of endomorphisms, and that naturally appears here. So each representation is given by an endomorphism, so I use a symbol for endomorphism. So lambda and mu are endomorphisms. Of AI arising from representation. Not any, there are lots of endomorphisms which do not arise from representation. Then, for this particular setting, it turns out that lambda and mu, they do commute up to unitary equivalence. So they are this unitary thing. Composition is equal to, so the composition lambda mu and the composition mu lambda are equal up to unitary equivalence. And this really is braiding. So this braiding structure naturally appears in this context. So in this way, we almost get a modular tensor category, but then we need, for modular tensor category, in addition to braiding, we need something more. That is, we have only finitely many irreducible representation, irreducible objects, and also so the braiding should be non-degenerate. So the asymmetric should be invertible. So we'd like to characterize when we have a modular tensor category. So this is naturally an interesting question. Then we have a complete answer. So we consider the following. We split the circle into 4 intervals, 4 pieces. The length don't matter. That's for disjoint intervals. Then we look at this inclusion. This is a von Neumann algebra generated by A of I1 and A of I3. Then we look at the other von Neumann algebra generated by A of I2 and A of I4. Then from locality, it's easy to see that these two von Neumann algebras commute with each other. So it means that if we take a commutant of one thing, then we get an inclusion. So this is an inclusion of a von Neumann algebra into another von Neumann algebra. It turns out that they are factor. This gives us a subfactor. Then, so this is a subfactor, but this is Jones. So we have the Jones index there, but this index could be infinite in general. That's completely possible. And this characterization for modular tensor category is given by finiteness of this index. This is old result. With long Huber and myself. So this finiteness is an important condition of some kind of finiteness, and this kind of finiteness is often called rationality in the context of conformal field theory. So this finiteness of the Jones index is our characterization of rationality for chiral conformal field theory.
Quick question. So,
Yeah.
if the index is infinite, it means you have infinitely many representations?
Yeah, sorry.
What if the braiding is degenerate?
And that's my second question is also, can
Can you have finitely many indivisibles braiding is degenerate? Or you could have
You have infinite index, yeah, that could happen.
that would have an infinite index.
Yeah, so if we have the infinite index for this subfactor, we may have infinitely many irreducible representations, or we may have infinite dimensional representation.
But only finitely many.
Yeah, that's right.
Does the index depend on the length of the interval?
No, it is independent of the choice of for interval. So we say that so this finiteness of the index is a nice thing. So this finiteness is called complete rationality. So we are basically interested in this, the thing, okay, I should define name, that's called a local conformal net. So this family of fundamental algebra is called a local conformal net. So one local conformal net means mathematically speaking, is one chiral conformal field theory. That's a mathematical setting. And we are interested in local conformal net with complete rationality. There are many examples of complete irrational nets, but there are also local conformal nets without complete rationality. So assume that suppose the family is completely rational. Then we have a modular tensor category of representations. Then here we can apply the machinery of alpha induction. So in this setting, we consider a family of subfactors. So basically, B of I is another local conformal net which contains A of I for each interval. So this is a continuous family of subfactors, and this is the notion of nets of subfactors. So suppose we have complete rationality for A of I, and suppose we have this inclusion, then actually this would automatically find the subfactor. So this is for each interval I we have a subfactor, which is basically independent of the choice of interval I. So we have finite index. Then so on this. So this is okay, n in the previous notation. Then in this setting, the dual canonical endomorphism. No, that's an endomorphism of the small algebra, and this decomposes within the Doppler Hard-Rober endomorphism. This is actually rather easy to see. Then we can apply the machinery of alpha induction. Then we get.
Should we get all of the DHR endomorphisms if we look at powers of the?
No, this depends on the subfactor. Because, for example, this might be equal.
Oh, yeah, okay.
Yeah, then in that case, of course, we get only the identity.
Yeah, same with the identity.
The DHR are the ones that come with the representation?
Yeah, right. So the dual canonical endomorphism comes from representation. So it's easy to see because this embedding is actually a representation. Then we have alpha induction for alpha lambda, alpha plus minus for lambda. So this is an endomorphism of n. Then so this is an induction machinery. So it basically means that in analogy to a classical representation theory, if we have a representation of a smaller object and we apply the induction machinery, we should get a representation of the larger thing, larger group. That should be a notion of the induction machinery in a representation theory. And here we have something similar. So here we start with, so lambda is, okay, so lambda is, okay, DHR. Of n. so comes from a representation from the smaller family A of I. Then if we apply the alpha induction, basically we expect that we get something like a representation of the larger family B of I. But
Sorry, so what's the Q system that you're doing alpha induction with? Is it M? Is it N?
yeah, any M.
So lambda actually comes from is one of the pieces of the dual canonical envelope.
Yeah, not necessarily. It can come from any representation. So previous question, some representation could be more general than those appearing in the decomposition of the dual canonical envelope. Then, so we expect something like a representation of the larger algebra, a larger family, but it's not exactly true. But we need some slight modification. So we look at the endomorphism. Appearing in decomposition, reduced decomposition of some alpha plus lambda. So we have these endomorphisms. Then we take the intersection with those alpha minus induction. Okay. So we look at those endomorphisms appearing in the decomposition of alpha plus induction, and we look at those appearing in the reducible decomposition of alpha negative alpha induction. Then it turns out that the intersection is really the DHR endomorphism of the larger up to unitary group. So in this way, this really, so we had choice of braiding for this induction machinery, but then, so if you combine positive induction and negative induction and look at the intersection, we really get this induction machinery in the usual, in the classical sense. So this is the meaning of positive and negative induction. Yeah.
Sorry, I thought that those would have these should be also should be modules for that Q system. Like it looks like so when you one thing is you take A lambda plus. This is like the image of the free module functor, and then you decompose back into the original category. You're having objects of the original category. So then it looks like if you're doing this, the object does it have some different type of tensor structure, I guess.
Yeah, here we have a composition of this one,
That one.
like so MM by module.
Yeah.
So this is in another setting, so it's called a local module, system for local module.
So, but it's not necessarily local.
Oh, okay, yeah, I was cheating a little bit. Okay, yeah, maybe we should assume this local, then, here we have a nicer situation. Yeah. So here actually we have an issue of locality of the large algebra. That's an issue of commutativity of the Q system or commutativity of a Frobenius algebra. And now we are cheating about that.
So when you say endomorphisms appearing in the decomposition, you mean the MM decompositions?
Yeah.
Okay, great.
That's right. So they are. Then, so if we have an extension of local conformal net, I mean a larger local conformal net, And this way we can study its representation theory through the alpha induction machinery. But then we can also determine or classify all possible B of I for given A of I, well, at least theoretically. This is the next topic I will explain. So this is a notion of a modular invariance. So say lambda mu irreducible DHL and what is A of I. Then we look at the alpha induction, positive induction, and negative induction. Then there are Mn bimodules, or endomorphisms of M, so we have natural notion of intertwined space, Hom space. Then we just count the dimension. So this is actually a finite dimensional thing. So then we set d lambda mu to be this dimension, so this is a non-negative integer. Then many other words that can cover and then be proofs. This is a so-called modular invariant. That is, this commute with the unitary the image of the unitary representation of SL2D arising from the modular tensor category of the representation of A of I. So this matrix D, so this is a finite set of finite remaining non-negative integers, so this is a matrix. So this commutes with D. S and T matrices, so S and T matrices are coming from this kind of picture. And also, the 0 is 1, so 0 is a vacuum identity representation. This is the identity. So each A of I acts from the vacuum Hilbert space. I mean the Hilbert space having vacuum vector. So that gives a representation trivially, and that actually plays the role of a trivial representation, and that's called the vacuum representation, or the identity representation. And we denote that representation by the symbol 0. So this is so lambda is 0. This is actually the identity, and it's easy to see that the alpha induction of the identity is also the identity. So identity for the 0, 0 is actually 1. Then, so we have this condition. So such a D is called modular invariant. Because I commute with the image of the representation of the modular group SL2D.
So the multiplicities are the first row is the one that gives multiplicities of the sum into the Q system. Is that what that's what the first?
Yeah. Okay. Yeah. Yes. I know. Explain that one. Yes. Then we also get the decomposition theta, the dual canonical endomorphism. Is equal to this one. But the lambda and the vacuum, the first.
It's only in the local case.
Yeah, okay, absolutely.
That characterizes.
Yeah, yes. Also, I'm assuming that everything is local. So if you know, we start by the locality.
So what does that mean? That yes, that's the same locality as the previous list of axes.
Yeah, so even if we have no locality for the extension, we can apply this machinery, and we still have
Yeah.
this is modular invariant.
So for the E7 molar invariant,
Yeah.
there is a BI,
Yeah,
but the theta would not satisfy
right.
that.
This is different.
But locality is something to do with the inclusion, or locality is just the normal locality assumption from your list of axioms? Is there
Locality
some-
for B.
Yeah, your locality of
Look, I
B,
assume
but-
for A, but
Yeah.
not for B.
Yeah, locality of B, but that also is characterized by certain condition of the Q system, the level of Q system, the commutativity of Q system.
So B wasn't assumed to satisfy all the axioms.
Okay, yeah, okay. I don't have it vague, I am cheating, but okay, I assume that B is also a local conformal net.
But sometimes you consider inclusions where the larger net it doesn't satisfy all the axioms, doesn't satisfy.
I mean, we have a general theory for such a case, but now I assume that the larger family also satisfies all the actions.
So now we can see exactly which DHR endomorphisms will appear in the decomposition. of
Yeah,
dual canonical
yes,
and-
that's the point, yes. So, so suppose that we have a completely rational local conformal net A of I, then we know a modular delta category. We have of representations of A of I. Then we have S and T matrices. Then, just from a general theory, it is rather easy to see that we have only finitely many modular invariants. Just abstract matrix V which commute with S and T and also satisfy that normalization condition, and also each entry of D must be a non-negative integer. So we have only modular invariants.
So is this like saying there are finitely many commutative algebras
Yeah.
in the category
Yeah.
that are like tall connected or?
That's right.
But you could have many algebras corresponding to
Yeah,
the same invariant.
Yeah, so
Right.
that's a transition
So
next.
what you said is strong.
Yeah, so actually, so on this level, we still have only finiteness of theta and the endomorphism of objects in the tensor category. But then we want to know finiteness of the Frobenius algebra or Q system, but the next structure. But then it's also known and fairly easy to see that for each modular invariant matrix B, we have only finitely many Q systems. So we have only okay, commutative.
I mean, this is true without braiding. I mean, in any fusion category, you're only going to have finitely many Frobenius algebras anyway. Right? I mean, the bound won't be very good, but
Yeah, that's right. But so this is our approach to finiteness of the one dimension. So in principle, there are they can be classified. So the examples of such classification following. Such classification. So the simplest or the most typical situation arising from so-called SU2 level K with the mean of the model. So in this situation, so K is positive integer for the level. So this corresponds to also quantum groups of UQSL2 at the root of unity, and also corresponds to a vertex operator algebra corresponding to the Kac-Moody algebra. But in the context of local conformalness, this family was constructed by Wasserman. And then, so, okay, irreducible representations labeled with integers 0, 1, 2, up to k. So we have k plus 1 irreducible representations. Then S and T matrices are explicitly known. Basically, S matrix is a trigonometric function, sine of something, and T is the exponential of something, sine something, and T is. They are explicitly known. And also the modular invariance classified by capital H from Gruber. Around 1990. And they are labeled with ADE Bunsen diagrams. Now then we need locality of the extent network commutativity of the Q system. Then we actually, so here those arising from the so-called type 1 modular invariance. That is A, B, even, E, 6 and 8 diagrams. So here again we have the same labeling of the classification of subfactors with the index less than 4. Also in that situation we have originally we have each AD thinking diagram as a candidate of the principal graph, but only D even and E6, E8 appear there, and here we have the same appearance of the same diagrams. So they, and then yeah, so they gives commutative Q system local. Which system and extension. Newton. And this kind of extension, actually all these extensions were known before. So in this context, this classification was given around the year 2000, but actually the corresponding extension of nets or extension of conformal field theory were known before. So they correspond to the following. Conformal field theory. So the AN diagram, so they are if you to level K minus 1. So G is the so-called simple current extension. If you do some K, then E6 and E8 they correspond to a so-called conformal embedding. Of SU2 at the level which 10 and 28. Yeah. So so if you know what the conformal embedding is, if you don't know it, but it's something given by.
Two less than this goes Coxeter.
Yes. So there, no, but we have so shown that they really exhaust all the possible extensions of the SU2 level cadence. Another example is the so-called mirror following. So in the remaining time, I first recall the Virasol algebra. So they are generated by countable remaining generators. That's an infinite dimensional real algebra generated by Ln and n is indexed by positive and negative integer, and C is the central element. And for among L, M, we have this is the defining relation of the real algebra. It turns out that this relation, so this gives all the Lie bracket among Ln, and so C is the central element, so the Lie bracket of Ln and C are always zero. And then it turns out that this really is the real algebra. And this is almost Lie algebra, infinite dimensional Lie algebra corresponding to the infinite dimensional Lie group, diffeomorphism group. But basically, we have to take the central extension of complexification of the Lie algebra corresponding to the infinite dimensional Lie group. So, nothing wants to give Lie algebra. Then, for local conformal net, we have skip details of the conformal covariance, but local conformal net. Local conformal net. We have projective unitary representation of the diffeomorphic group. Then, just like an ordinary case of a Lie group and Lie algebra, we can pass to representation of the Lie algebra. Then we get representation of the unitary in some sense. Bilateral algebra. Where C is mapped to a scalar. And this scalar is called the central charge. So in this way, we get a number, some number which is also written by C. And actually for the possible value of C is that which is 3, 4. So up to the value 1, we have a discrete series converging to 1. And then after that, everything is possible. So we have some formal similarity to the possible values of the Jones index. Then for this part is discrete, or discrete series. And in the case of the discrete series of the Jones index values, we have the classification of subfactor. And here we also apply this kind of alpha-induction machinery. Then for this part, we have a complete classification. Local conformal net. So we central charge for this discrete series. For this is so here we apply a similar machinery. Then we already have a classification of modular invariant again due to characteristics of Huber, and we have some certain pairs of ADE linking diagram. Then we have this complete classification of local conformal net under this strong assumption. Okay, so I stop here. Thank you very much.
Hey, thank you very much. Are there any more questions?
So you showed that for every extension of the conformal net, you get a certain type of commutative Q system.
Yeah.
And the converse is true as well if you have the right.
Yeah, that's right.
So the classification of the extensions of a given conformal net is basically classifying certain types of Q systems.
Yes.
Up to some
So
equivalence.
that's a
inside.
purely tensor category. So.
Yeah. And the last thing you did with the discrete series of central charge, was there an extension? Were there extensions involved there as well? You mentioned alpha-induction. Are you classifying extensions, or are you just classifying?
Well, we classify Q system, so we classify extension. Then it means all local conformal net central charge is actually their extension of the Virasoro net, which I didn't explain.
I see. Okay. But the Virasoro net is not. Is that?
Yeah,
not directly related to that.
Come from this representation.
Okay, but it's not directly related to the SU2.
Yeah, not directly, but somehow similar to it, arising from the coset construction involving the yeah.
Is the coset construction supposed to relate these two classifications?
Yeah, right. So this Virasoro, actually we have the Virasoro net arising from the representation of the Virasoro algebra, and they are realized by the coset construction for involving the SU2. Water tent poly construction, which can be formulated in this setting.
So this term local conformal net seems a little bit flexible. Sometimes it talks about, it refers to just AI.
Yeah.
Sometimes it refers to the extension AI.
Yeah, so in general, we talk about AOIs, but sometimes we fix one local conformal net AOI and talk about all net extending AOI.
Yes. This classification,
Yeah.
but the full CFT somehow should involve the modular invariant.
Yeah,
So it
that's
should
full
involve
CFT, so this is a chiral half. For full dimension, full conformal field theory, we have two chiral halves, and we have a modular invariant partial function, that kind of. That also can be formulated in terms of operators.
Any more questions? Thank you for your talks. So we'll meet again tomorrow with Roberto and Stefan Price.